Large language models are amazing in so many ways because they are the basis of building AI agents, building AI-based tools to solve real-world problems. But what happens is that most of these large language models, if not all of them, were trained on specific data, specific data sets, specific knowledge base. And so more than often, we want to be able to sort of retrain our model to a specific data set, specific knowledge base. And so there's a term for that, which is fine-tuning. So essentially is a way for us to take this large language model that was trained on this massive amount of data. So it's more of a generalizer. We want to make sure that we train certain parts of this large language model in this large language model so that it's specific to what we want. We might want to train or fine-tune our large language model on certain plant diseases, for instance, or certain wave patterns that we are collecting from the environment, or whatever that is. And so we have ways to do so, to fine-tune our model. And so in this mini course, which is actually part of a larger course that you can actually have access to, it's a really large course that takes you from A to Z about AI and large language model engineering. You can check the link in the description. I'm going to show you how to think about fine-tuning, what is fine-tuning, and how to fine-tune a large language model using different strategies and different tools. So it's going to be full of coding, full of concepts that you probably have never heard before, but I encourage you to stick around and go through it. And by the end of this mini course, you're going to be able to fine-tune your own large language models and see the power of extending the capabilities of large language models to power your own use case. All right, let's go ahead and get started. All right, so now we're going to embark on a different journey here. Still, of course, in the realm of LLMs and AI. We're going to talk about fine-tuning. And we're going to look at what is fine-tuning, the benefits, and why we would want to fine-tune a model. So fine-tuning, what is fine-tuning? You may have heard many places about fine-tuning, and you may even dabble a little bit with fine-tuning, but I'm going to give you an overview, a deep dive into fine-tuning so you understand the motivation behind it and how to actually fine-tune a model using different tools. So fine-tuning is the process of taking a pre-trained model. In this case would be GPT models or Llama models. So these are already pre-trained models that were trained on a large data set, and adapt those models into new specific tasks. So think of it like this. We have a pre-trained model. In this case would be a chef who has already mastered cooking and a wide variety of dishes like pasta, pizza, sushi, and so forth. And fine-tuning would be teaching the chef to specialize in a very specific cuisine, like Italian food, by refining their skills for that particular style. So essentially, I love diagrams. Large language models, in this case, have already been trained, as I said, on specific data sets, right? And so specific tasks, we can pass that through by fine-tuning through the models. That way, the large language model not only has the baggage, quote unquote, of what it has been trained on, but also now it contains or has access to specific tasks that we sort of have injected into it. So the question is now, why to bother about fine-tuning? Why do we care about fine-tuning? Well, for many reasons, we would want to fine-tune our models. Well, number one is for efficiency, because training a model from scratch is very, very, very expensive. Okay. And so by fine-tuning, what we're doing is we are reducing these requirements, because fine-tuning uses a pre-trained model already as a starting point, which reduces these requirements of having to pay a lot of money and use a lot of computing power to train from ground up. So this gives us performance. Okay. The reason why we want fine-tune is that we get a better performance because pre-trained models already have learned some useful features from large data sets, because they have that going for them. But when we have the fine-tuning side of things, so when we fine-tune, we're adapting these features to your specific task, often leading to obviously better performance. Also, data scarcity. So if you have a small data set, fine-tuning can be very helpful, can help you in this case achieve good results without needing millions of examples to train the entire large language model. Okay, so next we're going to look at fine-tuning techniques. Fine-tuning techniques. As always, we have techniques in everything that we do with large language models. And so fine-tuning, it's no exception. So let's look at some of the techniques that are very popular. So looking at fine-tuning, we have techniques, as I said, one of which is standard fine-tuning. We have low rank adaptation, also known as LoRA, and we have supervised fine-tuning, SFT, and reinforcement learning from human feedback, RLHF. So that's a mouthful, but that's what we have. Now let's look at the standard fine-tuning, what it means, how it looks like. Well, when you look at the standard fine-tuning, first of all, let's define what that is. What that means is that we have a process of taking a pre-trained model and adapting it to a new task by training it on a new dataset. Now, this process involves updating the weights of the pre-trained model to better fit the new task. So how would this work? So we would go, for instance, start with a pre-trained model such as BERT or GPT or any other model out there. And then what happens is that we add new task-specific head, okay, in this case, a classifier for text or images, as an example, and then we would train the entire model of, or in this case, a subset of layers, okay, on the new data set. And then we're going to use a smaller learning rate to avoid overriding the pre-trained weights. What does that really mean? Well, it means that as we're training these models, we don't want to override, per se, what is already there, what this model has been trained on. Okay, so that is a very important concept because that creates other issues, which we will touch on. Okay, the next one is low rank adaptation, which is the one we're going to be looking into in a few videos. So what happens here? Well, the idea here is very simple, is that we are going to make it so that we don't overdo things. The idea is that we are using this parameter efficient fine tuning. So instead of being too intrusive, meaning we are tinkering with the weights directly that are set in the model, okay, we're only going to add a small, very small, low rank matrices to specific layer, which means we're just going to be concerned about putting things or trained, updating those weights that are necessary to be updated, not the entire weights for the large language model. So what that do is that, so that will reduce the number of parameters that need to be updated. And if you look at the large language model, it has a lot of parameters. And so if we reduce the amount of parameters that we need to update, hence it's a low rank adaptation, which means we don't deal with the whole or the entirety of all of the parameters in a large language model. So the way this would work is, first we would identify the layers in the pre-trained model to adapt. So for instance, we could say the attention layers in the transformers as an example. And then we would add low rank matrices to these layers. And after that, we train only the low rank matrices while keeping the original weights frozen. Original weights frozen, that means we don't touch them. They just are going to be as they are. And then we combine the original weights and the trained low rank matrices during inference. Okay? And it's really important to understand when to use these different techniques per se. So in this case, for LoRA, low rank adaptation, a good use case would be when you want to fine-tune large models with very limited computational resources. Hence why we're going to use low rank adaptation or LoRA in this course, just to give you an idea on how to do this. Also, a good use case would be when you need to adapt a model to multiple tasks without having to store separate copies of the model. The other one is when you, for instance, you want to avoid what you call catastrophic forgetting, which means losing previously learned knowledge. Okay? So catastrophic forgetting is a very important thing to keep in mind when we are pre-trained or fine-tuning our models, because we don't want to lose the previous learned knowledge by the model. We want to freeze that to say, you stay where you are, we acknowledge you, but we are going to update certain weights through parameters in a certain layer, specific layer of the model. Okay, and then we have supervised fine-tuning, SFT. So this is when it's a technique where a pre-trained model is fine-tuned on a labeled, as they call, labeled dataset, in this case using a supervised learning. So the model, in this case, in this instance, is trained to minimize a loss function, right? This loss function is based on the ground truth labels. Now, there's a lot of keywords here, but what's important to understand is that this works as follows. So we would start with the pre-trained model, and then we prepare a labeled dataset for the new task. So a labeled dataset is essentially a dataset with all the labels that we can then pass through the training, fine-tuning. And then we add a task-specific head, example, a classifier or a generator, and then we train the model using supervised learning to minimize the loss function. And this kinds of technique, SFT, supervised fine-tuning, is really good when you have a labeled dataset for the new task, or when you want to adapt the model to a very specific task with high accuracy. That's a key point here. Or even when the new task requires precise alignment with the ground truth. And the next is the reinforcement learning from human feedback. Now, in this case here, as the name implies, is a technique. This is a technique where a pre-trained model is fine-tuned using reinforcement learning and feedback from humans. So humans are in the loop, as they say. So the model is trained to maximize a reward signal based on human preferences or evaluation. So there's going to be this feedback that will happen where human interaction, human feedback is indeed present. So how this works? Well, first we'll start again with a pre-trained model, and then what happens is that we generate outputs, for instance, text, images, using the model. And then we collect human feedback on those outputs, right? For example, rankings, ratings, summaries, and so forth. And then we train the model using reinforcement, hence reinforcement learning to maximize the reward signal based on human feedback. So when would you use such system, such technique? Well, it makes sense to use when you want to align the model's outputs with the human preferences, or when you need to fine-tune the model for tasks like dialogue generation or content creation, or even when you have access to human evaluators or preference data. These are the main fine-tuning techniques that are very popular. Let's now look at the comparison of techniques. Now, this is just an overview, and you don't have to memorize this. You can always look at this so that you have some ideas on the techniques versus key ideas and when to use them. Just an overview of what we've just looked at. So you can see here we have the technique on this column here. We have standard fine-tuning, LoRA, SFT, and RLHF. So the standard fine-tuning, we update all or some weights of the pre-trained model. Now, as you can see, this could be pretty intense, but when to use it? Well, when we have similar tasks, medium to large data sets. So this would be probably the best way to go. Then we have LoRA, low ranking, right? So what does it do? Well, the key idea is that we add low rank matrices to adapt specific layers. So when do we use this? Well, we use this when we have limited resources, we have multitask adaptation, and we want to avoid catastrophic forgetting, which means we don't want to mess with the knowledge base that is already inserted into the large language model. Okay, we want to maintain that. And then we have SFT. So this is fine-tuning idea here. The key idea is that we fine-tune using labeled data and supervised learning. So when to use it? Labeled data sets, If you have those, you have tasks requiring high accuracy. So this is when you would use this technique. And then we have RLHF. So this is fine-tuning using reinforcement learning and human feedback. So there's a human component to this. When is this aligned? When to use this? Well, aligning outputs with human preferences. Have that loop, human in the loop. Okay, if you have a system that requires that, then this would be the best candidate. Also dialogue generation, and content creation as well. Okay, so this is a comparison of techniques and when to use them. Just an overview of what we've just looked at earlier about these 4 techniques. Now let's look at a general fine-tuning process. So we know that fine-tuning is indeed the process of adapting a pre-trained model to a new task by training it on a task-specific dataset. Now, this involves updating the model's weights to better fit the new task. So here is a general overview of the process. So we have data or data sets that we go through the preparation process, right? Prepare the training data that we have because there are specifications that we have to follow. And then we add task specific, in this case head, in this case a new layer or new layers. And then we go ahead and start the training process, the actual train of the model. Then once that is done, we need to make sure that we evaluate to make sure that the things actually have worked. And then we're able to go ahead and deploy that model. And then that model is going to be able or ready for inference, right? So then we have this inference layer where we can call the model and start using it. Okay? So that is the general fine-tuning process. Now, right now, we are going to be using OpenAI API to show you how to fine-tune a model so that it is specific to a certain task that you need for it to be specific on. So the idea here is going to be the same. We have data sets. We go through the preparation phase. In this case, the format has to be what we call JSONL, or JSONL, I should say. And then that is what's uploaded into the OpenAI servers, because we're using their servers. And then we're going to create a fine-tuning job, or rather the API is going to create a fine-tuning job that is going to be running. And then we are going to go ahead and evaluate that model and then deploy the model. And then, of course, go through the inference layer. In this case, we're going to use OpenAI's completion endpoint to use the model and check it out, see how it works. Now, the thing to keep in mind here is there's cost, of course, associated with fine-tuning, just like with anything when we're using these closed source models. And so I have this link here to go check out the documentation about guides and fine-tuning using OpenAI. Let's go ahead and take a look at that in the next video. So if you go to that link that you should have access to, or you can just go ahead and say fine-tuning OpenAI on Google, and you should probably get to somewhere like this here. Okay, in the documentation. So there's a lot happening here, but what we're looking at is the fine-tuning side of things. So go to platform, click on fine-tuning, and gives you an overview of fine-tuning models for better results and efficiency. And you can see fine-tuning lets you get more out of the models available through the API by providing, number one, high-quality results, then prompting, ability to train on more examples and can fit in a prompt, also token savings due to shorter prompts. Because the idea is that once you have something that's fine-tuned, you don't have to create a more elaborate prompt because it's fine-tuned, so you can ask directly and get the response. And remember that tokens is the currency, I should say, for all of these large language models. So the larger the tokens that you're passing through, the more money you have to pay. Okay? So that is the whole idea here. Of course, we have all these things that they talk about at high level. Fine-tuning involves the following steps. We see this already. We saw this. Prepare and upload training data. Train a new fine-tuned model. And then we have this evaluate results and go back to step 1, right? Because this can be an iterative process, right? You test things, make sure you evaluate the trained model after fine-tune. And then if things are not working as needed, then we go back to the first step, okay, and continue use your fine-tuned model once everything is good. And so we have here a few models. Of course, this will change. It changes all the time by the time you watch this video. But the idea is that you know where to go to learn more about the fine-tuning process with OpenAI. The cool thing also is that we have this pricing page here. Let's go ahead and open it to see. Make this a bit larger. And so what happens here is that this is where you come in to see the pricing for instance, OpenAI O1. As we're recording this video, this is one of the models they have among many. And you can see that the price for input is $15 for 1 million tokens. So you can do the math and have output for OpenAI O3 mini and so forth. So let me find at the bottom here, fine tuning. There we go. So if you scroll all the way or search for fine tuning our models, you can see that we have the pricing here. Again, this changes depending on when you're watching this video and the model you're using. So for GPT-4o, fine tuning price for input is $3.75 per 1 million tokens. And they have the output is $15 per 1 million tokens, I should say. And training is $25 per 1 million tokens. So this gives you an idea on how things work. But you can see that for GPT-4 mini, fine-tuning is a little bit less. So it's 30 cents, I should say, for 1 million tokens. And then the training part is $3 per 1 million tokens. So considerably, so you can see the difference here, 3 to 25 if you're using GPT-4o. And for the input, $3.75, and here is just 30 cents. So it makes sense that you want to use GPT-4o mini in this case, right? Maybe by the time you watch this video, this would be lower. The idea is always to go low, of course, but maybe there's not a model where this is going to be way, way cheaper. In any case, now you know where to go and get all of that information. So in the next video, I'm going to take you through the process of fine-tuning a model, an OpenAI model, and go through the whole process so you know how to do that. All right, let's go ahead and get started. Okay, so let's go ahead and continue with the cost of fine-tuning using OpenAI. So the whole concept is that we have tokens. For instance, we have 90 tokens. That is going to go through the model, and then what that happens is that we are going to have API costs, and it's going to look at the prompt length and also the context window, which is how many tokens a model can process. And so what I'm going to show you next is to see or to go and look at the estimation, as we saw before, for our fine-tuning using OpenAI. First of all, number one, we're going to train the fine-tuning model. That's what's happening. And then we're going to use the fine-tuning model for inference. That's the part of the process. We visited this place already for the pricing, as I showed you, but now you have access to all of that. Okay, so the actual link. But I'm going to go forward here, but continue with tokens and characters. So there is this tool, if you go to the OpenAI tokenizer called the tokenizer, which allows you to pass in text, and then depending on which model you are inferring, it's going to give you exactly the number of tokens as well as number of characters. So let's go ahead and take a look so you can see exactly what's happening here. If you go to this tool here, tokenizer, you can see that it says you learn about language model tokenization. So it says OpenAI large language models process text using tokens, which are common sequences of characters found in a set of text. The models learn to understand the statistical relationships between these tokens and excel at producing the next token in a sequence of tokens. So this is essentially how modern large language models work. But let's go ahead and check it out. So in this case here, I'm just going to copy this text here, and I'm going to paste it all in here. Make this a little bit larger so you can see. So what happens now is I can toggle back from using GPT-4 mini and GPT 3.5 and even legacy. So if I go to GPT 3.5, if I scroll down, it's going to tell me exactly how all of this is created. So you can see for what I have here, the number of tokens is 34. And it color-coded everything to show you exactly how it looks at a text like this and how it counts the tokens, right? So this would be a token. This space and can is a token. This space and use is a token, and so forth. So tokens is not equal to characters, as you see here. We have 34 tokens, but we have 153 characters. Okay? And if you scroll down, we can look at text, token IDs, and all these things as well. But in any case, we can change. We can see for this case we have 34 tokens. And if I go to GPT-4 Mini, it's still the same. That is just an idea for you to understand how tokens work, how they are counted, and how it all comes together. I can clear, or I can also show examples. It gives us, adds here just a bunch of text, and then shows the tokens and characters and how all of that is set up. Again, you can go ahead and change, and we should probably see the same thing. Let's see, 54, 57. Looks like depending on the model, in this case, this is 53. But for this one here, it's changing to 57 tokens. So that's good, which means the less tokens we have, the less money we pay. So this is why you use different models, in this case, modern, newer models, because then the cost is going to continue to go down. All right, so that's what I wanted to show you. And in the next video, we are going to go ahead and get started actually looking at code and start this process of fine-tuning using OpenAI models. All right, so let's get started here. The first thing you will see is that I have this fine-tuning OpenAI, and I have this ft openai.py. So this is the file we're going to be working with. But also we can see that we have this tcrafter.json. What is this? Well, this is the JSON file which we're going to use to convert into a format that OpenAI fine-tuning system needs for us to get into so that it can actually work. Okay, so essentially it has these messages object or dictionary with system that says, for instance, this is a custom customer support chatbot designed to help with inquiries for tea crafters, an artisan tea subscription service, and all of that, and has a few pieces of information content pertaining to this fictitious business, tea crafter business shop. Okay, so we are going to build, in this case, create a model or fine-tune a model that could be used to answer questions pertaining to this tea crafter tea shop. All right. And so going back to our FT OpenAI here, there are a few things we need to install. Make sure that we have the OpenAI installed. We have also OpenAI data lib installed, as well as tick token and URL lib3. Let's go ahead and do that real quick. Okay, hit enter. And all of those going to go ahead and get installed. Okay, let's get started here. First, I'm going to go ahead and import a few things that we're going to be needing. First of all, we're going to need the OpenAI. This is direct OpenAI SDK. We're not using LangChain in this case. And then here, I also have pandas and other things that we need. But notice that I'm also saying load.env and passing directly define.env to read all local.env file. Now, because this is not going to be used as a variable, we just can put here an underscore. And so when we create the client, OpenAI client, we can pass the API key, getting from the OpenAI API key OS environment here. But as you know, that is inferred, so we can just not add this. But if you run into issues, you can always use it. So next, I'm going to put together some helper functions, but most importantly, also import, for instance, tick token for token counting, as we will see in a second. So we're going to use encoding here from tick token. We're going to use the CL100K based model for that. So that is what we need to encode everything, in this case, our tokens. Okay, let's start with the generation of JSON to JSONL. JSONL is a different format of data, different format of file format, I should say, that it's used for fine-tuning, in this case, a model in OpenAI, right? And so we need to do that. So I have the code that allows us to go ahead and create or convert our JSON file that we have this here. By the way, I used ChatGPT to create something like this. Okay, and then convert that to the right format, which is JSONL. Looks like I'm having some issues here, like this. Okay, so we're going to open the JSON file, which is going to be this guy here, and then we're going to return the actual object and load that into data variable, and then we're going to produce JSONL from JSON and using this code here. Okay, and that's going to be written, of course, once done, into our folder. Okay, we also need to make sure we check the file format to make sure it is congruent and it actually works. So I have code for that. So check for file format, we pass in dataset. It's going to go through the process for checking for errors, punctuation, and all of these things so that we can actually get the correct information out of all of that. Okay, the correct format. Okay, so next I have the num tokens from message. So this is for us to be able to count the number of tokens so that we can sort of calculate how much we're going to be paying or using, in this case paying to OpenAI for us to be able to use their API key to fine-tune our model. So it's very simple. I got from this OpenAI cookbook GitHub here, you can go check it out. So we pass in the messages and tokens per message and tokens per name. So we do all the calculations and then we return the number of tokens. Okay, so now what we're going to do is we're going to convert the JSON file into JSONL. Okay, and so we call JSON to JSONL. So in this case, we're going to go ahead and pass the JSON file, and then the output is going to be JSONL as such. All right, and then we're going to check file format. But for that, we need to pass, of course, the name of the file. And then we're going to load that file, this data path that we have here. And then we're going to initialize the data status or dataset stats so we can look at things. So I'm going to go ahead. This is going to be just for us to be able to see what's going on. So we're going to have first the number of examples, dataset, where we're coming in. And then the first example, we're going to go loop through and get all the datasets, the message from the dataset, because that is what we wanted just to see. Okay, just for us. And then, of course, we're going to go ahead and do format validation, because we want to make sure before we pass this along that we have a good validation, that the dataset is clean and ready to be used. Okay, so once we have that, we are going to do some calculations here for pricing. Now, this is just for us, again, to get the estimations for each conversation we pass through from our dataset, because dataset will have all this data. We're going to loop through and see how much this will cost. Now, the target epochs here is the amount of returns, is the amount of times that it goes through one cycle of going through these data as the training is happening. So we have a few variables here, and all we're doing here is printing the data set has, for instance, this amount of tokens that will be charged for during training and all that. So you'll see it's going to give us an approximation. Of course, I'm using this old school GPT-3.5 Turbo. This is the how much it will cost for 1,000 tokens trained using GPT-3.5. Of course, it's going to be probably lower than this if you're using, which we will be using GPT-4o. And then we're going to print the cost. Okay, so next we are ready to get started. Okay, so I'm going to go ahead and uncomment some of the code here. So now what we're going to do, we have the output JSON file, and we are going to pass that through the create function from our client, right? The OpenAI client, say files and create. So this is going to upload the file to OpenAI database, or in this case, backend. And then what we want to get this training file ID, which we're going to be using next. Okay, so let's go ahead and run right now and see what we'll get. We should get at least the training file, and we should get the JSON file created, JSONL, I should say, created here from the tcrafter.json. Let's go ahead and give it a run. Very good. So it went through, no errors were found when we did all of the checking. And you can see it gives us number examples 18 and this customer support. So it got a few things from our data set. And the data set has 1,437 tokens. that will be charged for during training. You will train for 5 epochs, right? So the amount of time we're going to go through each one of those documents as we train, and you will charge that amount. So it's going to be about 5-6 cents. So not a lot of money. Now, what's important here, we have this file ID here, which we need for the next step, right? Because the next step will be to create the actual fine-tuned model. But for that, we need the training file ID, which now we got. So I'm going to put it right there. So I put some things here. So we're going to start the fine-tuning job. So make sure that to know that this may take some time. So we got to be a little bit patient. But since this is not a large file, this should be fine. Now, what we need to do, we need to take this file ID that we got here, and we're going to copy that, and you need to replace it here. That's why we do this in steps. So make sure you get that file ID and replace there. Now, for GPT here model, I'm going to show you where you get the correct GPT model, because I tested before. If you go GPT 4.0 mini, it just doesn't work. So if you go to the documents, say docs, and go to fine tuning and go all the way down, you can see that which models can be fine tuned. So this is a good place to look at. So you can see the latest is here, GPT 4.0 2024. This, by the time you're watching this video, this may be something different, but any of these should work. If we want to be more frugal or just be retro in its essence, we can go ahead and get GPT 3.5 Turbo. That's fine. But for me, I'm just going to go ahead and use this one here. I should be fine. Okay. And so that's what I added here. And so once we run this, this is going to go ahead and fine tune, create a job, which is going to go ahead and start fine tuning and do all the things. So what we'll need to do then is to print that response ID, because that's what we're going to be using later for something else. So for now, I'm going to go ahead and comment this out because we don't want to run this again and go ahead and do the same thing. So I'm going to comment this out, and then I'm just going to run this, which we should get this response ID. Okay, so now we have this response ID, usually is FT job. This is the fine tuning job. That's exactly what we want. I'm going to copy that. Yours obviously is going to be different. And let's add a variable here. This is going to be job ID. I'm going to paste that one in there. Yours is going to be different. That's why we're running this in stages. And next, what we'll do, because this will take a little bit, we can even wait for a bit, but we can right away and get indeed the state of the fine tuning from here. To do so, it's very simple. We put into a variable state, we say client fine tuning jobs retrieve and job ID, which is this one. This is one again, why we are going step by step. And so let's make sure that I don't do the same thing. I don't want to create anything anymore. I'm just going to comment this out as you go. So once you have this code, actually, you can just run the whole thing from top to bottom. But since I'm running each time and putting code, I don't want to repeat things and break things. Okay, so I'm going to comment this out because I don't want to create another job. Okay, let's go ahead and run this. So this should give us something, the status of what's happening. So let's go ahead and print what we get, the status, because we need to get something from it, as you will see in a second here. Okay, so we have this payload here. So let's see, it says that fine-tuned model, none, because it takes time. Usually that means things are still working. But what I also want to keep an eye out is that we need this, because fine-tuned model is none, and also the model we fine-tuning is that. So job status, you can see status says running. So we should wait a little bit. And usually what I like to do is to run this again. And at some point, once everything is good, we should see something. It looks like it's still running. So we're going to pause and wait for a little bit. Okay, so it took about 3 to 5 minutes. And you can see I run again. You can see that status says succeeded. And the beauty, once you see that, you can see that we do now have this result list here. And there's this file name or ID here. This is what we need. So I'm going to copy this and go to our code, and I'm going to create a variable called result file, and it's going to be equal to that. Okay. So remember again, this is what you get once you've ran everything. Okay, get the job. So I'm going to go ahead and comment this out so we don't get that showing stuff again. Actually, if I go back here, since the success says status succeeded, you will see that also we have something else. We have this fine-tuned model, which is this one here. So this is actually the fine-tuned model. So I'm going to copy this right away and save it somewhere. I'm going to just put, say, like this, fine-tuned model. I'm going to add it there. Okay, but before we go there, let me go ahead and get this result file. So this is going to be a binary file. That means we're going to go and read it and then transform that into an object. And then we're going to use Panda to show us all of the contents of that file. Here we are reading in this file that we get, right, from our result file. It's a binary, and then we're going to get all those bytes, transform that into something that's an object, and then we're passing that to read as CSV to the data frame. And then we're going to PDF, and then we're going to print that so we can see what's going on. All right, let's see. I don't want to repeat anything here. Let's go ahead and see what will print out. You know, sometimes happens where you get this gibberish here, and I notice maybe is because things are still happening in the back end. I'm not sure. So let's see if we continue this. Let's give it a few moments, because sometimes it takes a while for it to actually get the pieces, because now it's just showing these bytes here or a different format. All right, so sometimes you will get something out of this read CSV file. I waited for a bit, but sometimes you don't. It's okay. It should be all good anyway. So we have our fine-tuned model here. Now we're going to go ahead and evaluate and test things to see if it actually works. So the first thing I like to do is I'm going to start with evaluating the GPT-4o Mini. So I'm going to ask questions pertaining to our data, and which means that GPT-4o Mini would have no clue about this. So I'm calling the create completion endpoint, passing GPT-4o Mini or any model for that matter, and then I'm passing this what types of T's are included in the subscription. Most likely this is going to hallucinate, give me a random response, or a I don't know, but most likely it's going to be hallucination. Let's go ahead and run this real quick and make sure that all is good. And yeah, let's go ahead and run this. Okay, you can see that this is totally hallucination. It says the types of T's include all of these, which is literally a lot of hallucination here because because it's just too much, even though some of these are there, but it's not correct. All right. So now I'm going to do the same thing, and I'm going to use our own model, right? The trained model or the fine-tuned model. And I have access to that because remember, I have this fine-tuned model ID. I'm going to copy that. You should have your own. And I'm going to replace that here with that new one. So now you can see I'm using the fine-tuned model. Everything else is the same, including in this case what the question that I'm passing along. Okay, let's go ahead and run this and see what we'll get. And the other thing I have here, and I put this fine-tuned response, that way we can see the difference. Okay, let's see if this is going to work. Now remember, because when we use a fine-tuned model, it's really direct and gives us exactly the information that we need. It doesn't need to hallucinate and make stuff up. Let's see if this is going to work. Very good. And this is wonderful. So it says here, for the fine-tuned, it goes straight. So our T subscription includes a variety of T's such as black, green, herbal, oolong, white, and specialty blends. Each month selection is curated to offer unique flavors and experiences. So I'm going to go and get, for instance, I'm going to copy this and see perhaps the language has changed a little bit. Let's go to tcrafter and I'm going to say Command F and I'm going to paste that. Doesn't show anything, that's okay. And say subscription, nothing. Let's see oolong. Oolong, and you can see that indeed we have oolong, white, green, black, and it says here also artisan teas that are blended there that we get. And you can see it says specialty blends, which is exactly that we're getting here as well. And also each month features curated selection based on your preferences. Okay, it's actually working. It's getting something that is directly from our fine-tuned model, which is we fine-tune with pieces of data set. So I'm going to ask this question here: how do I change my tea preferences for the next month, and see what it's going to do? So I'm going to do for both of them. This one and this second one here. Let's run. Okay, so this first one here is total hallucination from GPT-4o Mini. And then we have the fine-tune model to change your tea preferences for next month's shipment. Log into your account on the tea service website and update your preferences under subscription and all of that. And we can try to confirm that this is also not hallucinating. It may be, because you never know. And if we go to tea, voila, you can see it went and got exactly. You can update your tea preferences, change your tea preferences from the next shipment, log into your account on the tea service website and update your preferences under the subscription. Okay, there we go, subscription settings. Wow, nice. Make sure to save the changes. Changes must be made at least and so forth and before the next shipment. So it works, right? It's getting exactly the information that our assistant knows how to answer because it was trained and fine-tuned on this information. All right, so that is the basics of fine-tuning using OpenAI models. It's a little bit involved, but follow those steps and go through stuff. And notice that sometimes it may take a little while for you to get the actual fine-tuned model. So be patient with this and keep trying, and make sure also to comment pieces of code as I was showing you here. That way, when you keep running like I'm doing, you don't override or overdo certain things. Okay, when you see this code, I'm going to uncomment everything so that you have the code in its entirety, but make sure that you will have to go step by step because you need certain files like files ID as you go through to make this work. You can automate this, make it better, of course, by just passing in the results and passing those variables along, but I just want to show you the whole process. Okay, so now let's take this to the next level and create a chat box using the interactive loop console here. Nothing really crazy, but something to give us some sort of a nice satisfaction here, because we have our model that is trained, maybe not the best training, but it is trained and it works at this point. You can test on your own to see what results you get. And keep in mind, if you're not getting the right results, it's always important to go ahead and retrain by passing through this whole process again, and maybe up the epoch that we have created here. So epochs 5, you can add more, maybe 7 or 10, but usually 5 should be good. All right, so let's go ahead. I'm going to show you exactly what I have here. Okay, so I have this fine-tuned, and I'm going to use this context here. This is a customer support chatbot designed to help with common inquiries for tea crafters. All right, so I'm going to have the collect messages function to keep track of message exchange between the user and assistant. And I have this function get completions to help us. So I'm going to use fine-tuned model, which is what we have at the top here. You should have your own. Okay. And so we're going to start the conversation between the user and the AI assistant chatbot. Okay, let's go ahead and run this real quick and see what we get. Okay, so it's running the previous things that we had before, but then we get to the point that we can see, hey there, how can I assist you? What is the name of your shop? Let's see. There we go. We are called Tea Crafters. How can I help you? How does your subscription work? Our subscription sends a curated selection of tea every month. You can choose your preferences and we'll tailor the box to suit your taste. Adjust or cancel. Okay, let's see. I'm going to copy this subscription just to make sure that we're not hallucinating here too much. And look at this. So this is customer support. So our subscription includes varied artisan teas, all of these curated selected boxes. Very good. Okay, let's see. I'm going to ask another question. Can I skip a subscription? A month subscription. Let's see. Say absolutely. You can pause your subscription and skip a month by logging into your account. Look at that. That's exactly. You can skip by logging into your account and selecting. It doesn't go further, but that's okay. So it is indeed working. And let's see, how do I cancel my subscription? You can cancel by logging into your account, visiting the subscription setting page, cancel anytime, no. Very good. Settings, click cancel subscription and follow and everything. Okay, I'm going to ask, what is the sourcing process of your teas? Okay, look at this. Our teas are sourced directly from sustainable. Teas sourced directly from small sustainable tea farms around the world. Very good. We prioritize quality and ethical sourcing and work closely with our partners. Okay, very good. So you can see that this is actually working. It's not hallucinating, and it's giving us the correct information because we trained, or in this case, fine-tuned this model. All right. See if you are getting these results, and I'll see you next. All right, I'm sorry to interrupt. I just want to let you know that this is actually part of a large course that I put together called AI and LLM Engineering Masterclass. So the idea of this course is that if you have never heard of AI or don't know much about large language models, this course is going to take you from literally zero to heroes to understanding what is AI, how large language models were built, how to fine-tune large language models, how to create RAG system, what is a database, what is a vector database, what are embeddings, what is a transformer, what is the transformers library, and all the things that I wish I had access to when I first started with large language models and AI and all of that. I put all of that in this huge, large, big course that is about 28 hours. And if you don't know Python, don't worry. I also include all of that in the course. So it's a full-fledged course, complete course of 28 hours or so, where you're going to be immersed into AI engineering and large language models and building and understanding exactly these new large language models and AI in general. If you're interested in the full course, there is a link in the description where you can go and get the course at a huge discount. So let's go back to the course. So now we're going to look at fine-tuning hands-on with LoRA. So we're going to now use open source models to learn how to fine-tune, which means we're going to have a little bit more of hands-on to get our hands dirty into understanding how to do that. But before we continue here, we need to understand what is that we're going to be looking into. So we're going to look at LoRA deep dive. So we're going to understand what PFT is, in this case, fine-tuning large language models with LoRA. So let's get started here and see what is PFT. So this idea of PFT. So the idea is very simple. PFT, is parameter efficient fine-tuning. So it's a technique for fine-tuning only a very small subset of a model's parameters. So what does it do? Well, it allows us to reduce the memory footprint and computational costs. So, as you know by now, fine-tuning, training a model, it requires a lot of computational resources. And of course, it's very, very expensive. Okay? And so by using PEFT as this technique for fine-tuning, we are only dealing with a very small subset of the model's parameters. So we're not dealing with the whole plethora or the whole bunch of parameters that a model holds. We're just focusing on a very small segment. Now, you may think that, okay, if we do that, which means we're just using a small subset of models parameters to fine-tune, you may say, well, maybe the results are going to be very minimal. Well, that is not true. The whole idea here is that all that is going to happen, which means we're going to reduce the computational costs and memory usage, but we'll still achieve good performance on downstream tasks. Now let's look at some benefits of LoRA. Now LoRA, remember, is low ranking adaptation. So here are some benefits. Number one is that we have parameter efficiency. What that means? Well, that means with LoRA, we are adding only a very small number of trainable parameters. For example, 0.1% of the original model's parameters. So very, very small a sliver. So a very, very small amount that we're dealing with. And so what this does, well, it makes fine-tuning feasible on smaller hardware setups. So i.e. on domestic computers such as the ones that most of us have access to. And two, we have memory efficiency because, as you know, most of the model's parameters are frozen. LoRA, in this case, reduces memory usage during training. And also we focus on the task-specific adaptation, because LoRA allows the model to adapt to new tasks without overriding the pre-trained knowledge. This is very important because we don't want to mess, quote unquote, with the pre-trained knowledge that is already in the model. Also, we have scalability. That means LoRA can be applied to very large models such as GPT-3, GPT-4, BERT, and so many without requiring massive computational resources. So all in all, the benefits we get with LoRA is that we have this parameter efficiency, memory efficiency, task-specific adaptation, and scalability. Now, when to use LoRA? Well, we want to use LoRA when we have very limited compute resources. You have no access, in this case, to these high-level GPUs and TPUs, then this would be a good candidate. When we have multitask learning, or we want multitask learning, in this case, we need to fine-tune a single model for multitasks without storing, in this case, separate copies of the model. This will be a good technique to use. Also, if we want to avoid catastrophic forgetting, what does that mean? So we want to be able to retain the pre-trained knowledge while we're also adapting to new tasks. Now, catastrophic forgetting, it is a huge deal because that means we don't want the model's knowledge base that it was trained on to be messed with. If you want to avoid that, then LoRA is the best way to go. Let's do some deep analysis when it comes to LoRA. And I always like diagrams as well as using analogies. So here's a diagram that sort of gives us this LoRA deep dive analysis. So at the top we can see we have LoRA implementation, and I like to use analogies, as I said, and I want you to think of LoRA, low rank adaptation, like a master chef who is refining a classic recipe. So what happens is that the chef wants to perfect a dish. So what he does? Well, he has, in this case, a base recipe. So we will have a pre-trained model like a classic dish that's already good. And he would have spices, right? In this case would be LoRA parameters, which are small additions that significantly change the flavor. So these will be the spices, the LoRA parameters. Okay. So got balancing flavors and adding spices. Okay. So this will be a kitchen analogy. So the technical aspects of that is that we have, in this case, overfitting versus generalizability. We have rank selection and parameter tuning. Now, lots of words here, but it's okay. We'll dive into them. So when we look at this model training, we have the overfitting side of things and the generalizability. So what happens? So using this analogy, when we talk about overfitting, we could use an analogy that says it's like a dish tailored to few people. What does that really mean? Well, it means it learns training data too well because it has to be very specific to tailor to a very specific people. Now, in this area here, if we go to this level here, which is the generalizability, this is like a dish that pleases everyone. So everyone likes the dish. What does it mean? Well, performs well on a new data. That means then if we were to serve this to everyone, most people, if not all of them, would like this dish. If we look at overfitting again, it's like, again, a chef who creates a dish that's perfectly suited to any customer's exact preferences. So it's too specific, won't appeal to others. It also has this limited usefulness. If we look at the generalizability, it's like creating a dish that most customers will enjoy, which means it has balanced flavors, it has broad appeal, and is versatile. Now, if you look at, for instance, the overfitting signs, so overfitting would be great for cases where we want this perfection, right? We have this perfect performance on trained or training data, but also poor performance on new data. Okay, now let's look at this deep analysis of rank selection. So when it comes to rank selection, we have low rank and we have higher rank. For lower rank, we have fewer parameters, prevents overfitting, as you know what that means, and also limited learning capacity. When it comes to higher rank, we have more parameters, better learning capacity, risk of overfitting. What does it really mean? Well, think of it rank like choosing the right kitchen tool. So if we have a lower rank, it would be like using a simple knife. So we'll be able to do basic things, right? It's basic, but it's reliable. So we have just a knife that does what it needs to do. But the thing is that we have limited capabilities because it's lower rank. It's just a normal knife. We also have less chance of mistakes because it's simple. We know exactly what to do with it. It has one purpose. Now, when it comes to higher rank, think of it like using a very complex food processor. It's more capable, but also more things can go wrong because it's a little bit more complex. On top of that, it requires more skill to use effectively. So those are the two differences of lower rank and higher rank when it comes to this rank selection. So keep in mind, lower rank, like using a simple knife, it's basic but reliable, it's limited capabilities, it's also less chance of mistakes because it's very simple. Higher rank, on the other hand, it's like using a very complex food processor. We have more capabilities, more things can go wrong, obviously, because it's complex, which means it also requires more skills to use effectively. So now let's look at parameter tuning. So when it comes to parameter tuning, we have learning rate, batch size, and number of epochs. So what does that all mean? If we look at the learning rate, we say too high, quick convergence, too low, slow training. Okay, I like analogies again. So learning rate, you think of it as like adjusting stove temperature. So if you have high, or if it's too high of temperature, that means food is going to burn, which means model diverge. If it's too low, what happens? Well, it takes forever to cook. So slow training. So that's how you would think about learning rate using our cooking analogy. Now, if we look at the batch size, we have large batch size, stable but memory intensive. Small batch size, we have less memory but unstable. Well, let's go back to our analogy, cooking analogy. This will be like cooking portions, which means if we have a larger batch cooking for a party, for instance, it's stable, but it's very resource intensive. Lots of work has to go into it. But if you have a smaller batch cooking for one person, it's more efficient, but of course, less consistent. Now let's look at this number of epochs. What does that mean? It's like cooking time. So too few of these, which means we're going to have undercooked food. This is what we call underfeeding. If we have too many of that, that's going to be overcooked, overfeeding. Now we want to have just right, which is going to be perfectly done, which is what we call optimal training. So these are the pieces that we need to understand so that when we start doing the actual LoRA implementation, you will have some ideas. Now, this is not a full course, obviously, on LoRA, or for that matter, on fine-tuning, but I'm just giving you some options so you understand what all of this entails. Now, let's go ahead and look at implementation strategy. So here we have at the top LoRA implementation. We go through the initial setup. We're going to choose low rank. You understand what that means. We're going to set default parameters. We start the training phase, monitor performance, adjust parameters, go back in this cyclical adventure that happens here. Training phase, monitor parameter, monitor performance, adjust parameters if need be, and back and forth until we get to the maximum result. Looking at this as a restaurant opening analogy. So like opening a new restaurant, you go through the setting up phase, like preparing the kitchen, initial menu, in this case, start with basic dishes. We have customer feedback, monitor, in this case, reactions, and adjust, which is the refinement of recipes based on feedback. So that would be exactly how we would think about if we were using a restaurant opening analogy. Okay, so we've done a lot of theory here, so we should have some basics, fundamental understanding of LoRA as a technique, a fine-tuning technique. Let's go ahead and go into code so we can see how to at least start implementing all the things that we've learned doing this walkthrough. So we're going to go ahead and do some hands-on now. So now you should have this fine-tuning LoRA directory with LoRA text simple or simpler as the first file. So we're going to do some importing here. Keep in mind that this is going to go fast, and there are a lot of moving parts here, but I'm going to go slow and explain what's going on. Okay, and the idea is to give you some overview on how to do fine-tuning using LoRA technique. So we're going to import a few things here. I'm going to go ahead and get all of them. And the first thing you can see here, we have OS, Torch, NumPy, and we need to import datasets. So what is this? Well, this is a library that allows us to pull in datasets from different places, but most importantly from Hugging Face and other places, okay? So load datasets that we can use to facilitate our training. And also we need to get the PEFT, right? That is the technique we looked at. So this is actually a module that allows us to import LoRA config, get PEFT model, and all these things. And we should have transformers by now, so we're going to get a few other modules from there. And of course, evaluate. Okay, let's go ahead and say pip install. I'm going to start with datasets. And something else that we need here, put this smaller here so we can see. And PEFTs, as well as evaluate. Now, I'm not sure if I can just get evaluate myself. Let's say evaluate. Let's hit enter and see what will happen. Should be probably PEFT, not PEFTs, I believe. Okay, very good. So we got all of them. I'm going to add all of these dependencies, of course, into requirement text, that text I should say. So let's start with a few functions, utility functions. So we have this print model size. I'm going to add a path, and this is just going to be something to help us to print the model size if we need to get that. So this model size are going to be actually added locally, as you will see. And then we have this print trainable parameters. So we're going to pass the model and the label. So these are just something that we're going to be using to look into what we're doing. Okay, so next, let's go ahead and find the function where we're going to build LoRA model, the actual model. Now, there's a lot of code here that can be a little bit strange, but let's go ahead through it and see. And so here we're going to pass a few things. First of all, we're going to go ahead and get the actual model. We're going to use the auto model for sequence classification and get the function from pre-trained. And we're going to pass the model checkpoint here. Now, the model checkpoint is going to be, I'm going to use, in this case, a Dilbert-based uncased model. And so I'm just going to go ahead and add it something at the top right there so we can actually use that. Okay. And so what we're going to do then, we're going to use the print trainable parameters, passing the model, and the label is going to be base model. This is the function we created earlier. And then we need to create what we call the LoRA configuration object. So there's a few things that we're passing here. If you hover over, you can see we have parameters such as task, heft type, and all these different things. But we also have R as int 8, as you see there. So what I like to do sometimes is to read what all these arguments mean. So R as an int, this is LoRA attention dimension. This is the actual rank. Okay, we're passing 16 in our case here. And let's continue here. Let's see what else. Then we'll have LoRA alpha. It's also an integer. This is the alpha parameter for LoRA scaling. Right? So we have all of these different parameters that we're passing in so that when LoRA is ready to start training, doing the fine-tuning in this case, it will know which parameters we need to pass along or set up for this to work. Now, there's a lot here, but that is exactly what's happening here. So we need to have this LoRA config function and passing all these parameters. Okay, and then we get the LoRA model. We get that by saying get heft model, passing the model, and the LoRA configuration, which we set up here. And then we're going to just go ahead and print the parameters, passing the LoRA model, and the label is going to be LoRA as such. In this case, we're going to go ahead and return the LoRA model. Okay, next we have this preprocess function, which we pass examples and tokenizer. So we're going to preprocess or process the text that comes in this case, right? We got to get examples and we're going to get the text out of that, strip everything out and create a list of a string, which is going to be, in this case, text, right? And then we have the tokenizer. So we're going to tokenize the text. So we're going to use the tokenizer object in this case, and then we're going to pass the text, truncation is true, and max length 128. So what we do then, I'm going to return the label. So this result here, once we run in this tokenizer to create the tokens that are needed, we have the labels index or field. So that's when we're going to add those labels into our result. And once we're done, we're going to return the result itself. All right, so that's about it. So now I'm going to have the part where we're going to run everything and see how it all works. Okay, so I have here starting LoRA fine-tuning demo, and I have this checkpoint. In fact, I can just comment this out because I added it at the top. So first thing we're going to use, we're going to say print here. We're going to say the model we're going to be using. So using model, the model checkpoint, which is going to be this as we put it before at the top. And then we're going to load all the dataset because we need datasets. So what dataset are we going to be using? Well, when we instantiate the load dataset is a class or function that returns a lot of different datasets that we can go and get. So in this case, we're going to get the IMDb. This is movie directory with actors and movies and what about the movies and all that. And we're going to just go ahead and pass and split. So we're going to just get about 1,000 of the items of movies or whatever we're getting from IMDb, just 1,000 of them, because that should be plenty. Okay, that's the dataset 1. And dataset 2, we're going to do, again, load dataset. We're going to use AG News. We're going to go ahead and get 1,000 pieces of data for our dataset 2. Okay? And so here we're going to print out the size of each one of the datasets, I should say. So we're going to say dataset 1 size, the length of dataset 1, and example. So would say dataset 1 size is 150,000 examples that were put through. In this case, it will be about 1,000 at least. And once we do that, as you know, we need to prepare that dataset, right? So in this case, we're going to label them. So we're going to take dataset 1 and rename the columns. We're going to have label and labels. So we're setting everything up so that it's easier for them to pass that through the model to start training. Here we're splitting the data sets. Okay, so we're going to use this variable train size. We take the first data set, in this case, the length, and multiply by 80%, which we get the integer. That's what we're going to be using that as a multiplier in this case. And we take each one of these data sets and we split those data sets, passing, as you see here, say data set select and passing in the train size as the range. So we do for all of them. We have train, the test, train, and test. All right, so then we're going to print here loading tokenizer because we need a tokenizer, as you know, because we have to create those tokens, which are the ones we're going to be passing through the large language model, or the model in this case. So to get a tokenizer, we say auto tokenizer. From pre-trained, we pass the model checkpoint, which we know it's going to be distill base uncased, right? That's the model. And then we create the data collator. So we say data collider. If you hover over, it's going to tell you what that does. So data collider, that will dynamically pad the inputs that are received. We need to pass tokenizer as the values. Okay, so now we have the configuration dictionary. So this is what we're going to be passing along. So what we're saying here, for the sentiment, we want to train data, use the dataset 1. The dataset for testing is going to be dataset 1 for testing. And we pass number of labels is 2. The epochs is going to be 5. That means we're going to go 5 times through all of the dataset. 1 run, 2 run, 3 run, 4, and 5. So all through that, each one of those datasets. Okay, and the path, once everything is done, we're going to put under LoRA sentiment. So we're going to create a path where after training the model, we're going to put under LoRA sentiment. And we're also going to train on the topic. So in this case, we're going to have train data. First here is going to be dataset 2 train, and the test is going to be dataset 2 test, and the same thing. And for that, the path, once all is done, we're going to call LoRA-topic. All right, next we have the processing datasets. So this is where we go through the process, of course, of processing each piece of dataset, mapping all around, making sure everything is as it's supposed to be. But most important here, then we have the training arguments. So we can now pass all these pieces, as you see here. We can pass a lot if you hover over. We can put output directory, do train, all of these things here that we can pass along, okay, as parameters to set up. So there's a lot. It tells you what it takes to actually train and fine-tune models. So specifying exactly certain things that we are going to include as we train these models. Okay, then we have the metric. We're going to use evaluate and load the accuracy. So we get the metrics. And then we're going to compute the metrics, the predictions and everything. Okay, we go through all that process. And the trainer here, we instantiate the trainer function, or rather the class, which requires the model, needs the training arguments that we set up at the top here. So we're putting everything together now. The trainer is going to train everything. Train data set, we know to get that from train data and test data for eval data set, the collider, the compute metrics and everything. And then we say train that train. This is where everything happens now. It's going to start training because we have all the pieces together, start the process of training and go from there. And then we get the eval results from trainer.evaluate. So this function is going to return all the metrics. And then we're going to show those metrics here as well. Okay, we're going to save the model through the pass and then print model size. So we can see the differences in size from when we started and from we ended. Okay, there's a lot, but we also have the predict text here. This is going to allow us to pass text, model path, number of labels, and task type. And we're going to use the from pre-trained and pass in the model check and the number of labels. And of course, we're going to instantiate the model. We're going to use the PFT model and pass in the base model and the model path. So it knows how to find the model path that was pre-trained right now and go from that. And then we're going to go and call model.eval and then have here inputs. So we're going to look at tokenizer, which gets, we have to pass in the text, and then we have truncate to true and max length 128. So we're setting up the tokenizer. And all in all, we are making sure that we have, for instance, label set up. So we have this label map. So 0 is going to be negative and 1 is going to be positive for the sentiment analysis. All right. And the label map is going to be world, sports, business, science, technology. So this is part of the second data set that we pass along, aside from the IMDb. And then we return the label mapping for predicting class and confidence and all of that. So that's going to be used in a little bit. All right, and then we have these test samples or examples here because we want to test the models that were created to see if they actually are working. Okay, so we have the texts here. We have, for instance, the text that we're going to pass along. For instance, this movie was absolutely fantastic. The acting was superb. Model is going to be sentiment. We want to use the sentiment model because remember, we're training 2 models here. Okay, sentiment and topic. And then number of labels, we have 2 for each one of these. Task type is going to be sentiment. Expected is going to be positive because this movie was absolutely fantastic, should be positive. Okay, and the next one here is the worst film ever, sentiment, all that stuff, and expected is going to be negative. right? Because it says worse. And then we have the other one here related to model topic. Tesla stock surged 25% or 20% after strong quarterly earnings. So we expect this to show us when we run under topic model, we expect to get business, right? And all of that. The other one for science and technology. Okay, so here is where we then run prediction on the test examples. So we're going to take all of this payload, all these texts, and run through and look at the actual models for each one, go to the path to get the models, and then start printing out the prediction for each one of the texts that we're passing through. Okay, and using different models, the topic, as well as the sentiment analysis model, and see how it performs. So I know this is a lot. The basic idea is that this is how we will go through the process of loading the models that we want to train, and train in this case on two things. In this case, we have the topic as well as the sentiment analysis, and then we're going to be testing. So that's what we're going to be doing in the next video, the actual testing, where you can actually see how to train this, run this code, and see the whole thing happening. Okay, so let's go ahead, time of the truth here. Let's go ahead and run this and see if this will work. So Python 3 and LoRA text simpler.py. So this should go through the process of first loading the model, right? BERT, I think that's what we're using, and go through the process of loading the datasets. And it's going to use the distilled base and case, distilled BERT, I should say, base and case, so a very small model. Okay, and it's going to go through the process of doing all these pieces here. So we're going to go through all of that, and at the end, hopefully everything will look great. Now, you need to look at what's happening here. So this number here where it says loss, we want this number to keep going down and down and down, which means the training is actually happening, and it's a good thing, right? So if this number, as you see here, it started really high, 3, it's going through the permutation, it's going through the process and everything of training. At the end, it should continue going lower and lower. And at some point, you can see that the first one here, evaluation accuracy, 1%, this is 1.000, so it's 1, that's pretty good. Model size is 4.7 megabytes. So the model is small once it's been trained, first one. And now it's training topic classifier. So some weights, the still BERT sequence were not initialized, and some issues we're getting there, but it's okay. It says you should probably train this model on a downstream task. Okay, but these things are happening here. It's going down this number here, the grand norm. Going through the same process, the training process. You can see evaluation accuracy is about 0.8, so a little over 80%. Okay, so this one, you can see evaluation accuracy is 0.8. So this is 82% about. Okay. Okay, and then we ran some predictions here. So keep in mind, when you train, things may not work as expected. But now we're going to run some predictions on tests example. All right. So the text we passed along was, this movie was absolutely fantastic. The acting was superb. Expected is positive, and predicted was negative. So this is not good. It means maybe we need to do some more training because it wasn't able to pass on that one. The confidence that the model, the evaluation comes is 99.7%. So it's very confident that this is negative, which is not true, right? But that's part of training. And you can see this one, the worst film I've ever seen, complete waste of time. Predicted is negative, and predicted, I should say expected is negative, and predicted is negative. So this is good. Confidence 99.82%. So you can see it fails a little bit in some cases here. Failed to say that this was actually positive, but it is actually passing here at 99.82% of confidence, which is true. So it did a good job at predicting there. Okay, the next we have Tesla stock surges 20% after strong quarterly earnings report. This expected. The topic is business. Predicted, voila, is business, which is 92.07% confidence, which is great. That means the model actually predicted correctly. That's real good. And then let's see. We have the next one. New AI model achieves breakthrough in protein folding. Expected is science and technology, and predicted indeed is science and technology. So essentially, we failed at just one in one of these predictions here. which was about the movie being absolutely fantastic, and the expected was positive, but the predicted was indeed negative. All right, so that's it. And if you look at what we get after all this training, let me show you exactly what's happening. So we can see we have these folders that were created. So we have these checkpoints. So we have about a lot of checkpoints, you can see, right? So these are actually files, as you can see, that safe tensors. These are files that are used to actually create, or part of creating the actual models, right? So these two, we have LoRA sentiment and we have LoRA topic. So these two folders here, this is what contains all the trained information that puts together into a model. So these are actually used as models for sentiment and for topic analysis. That's it. So now we have two models that we train them on two different data sets, and they're working. Okay, very good. Now, it may seem like a lot has happened and a lot of confusion here, but that's exactly how you would do it. The important thing here is to learn how to read what's going on. So I'm going to go back to let you know. So as the training process happens, we have this eval accuracy and everything, and the sample per second, 108 per second, and all of that. Right, so we do have all the metadata about the training, and the epoch, which how many times it went through the process of going through each one of these data sets in the training process, was 5.0, which is 5 times. So you can see that we have a lot of more information here. If we go up, you can see we have this base model trainable parameters. These are the trainable parameters. 66 million, almost 67 million over 66,955 and 10, which, as you see here, is 100% of trainable parameters that were trained. So LoRA, in this case, trainable parameter is this much over this much. So the idea here is that 1.73%, that was the fraction of parameters that were trained in our model. That's why it was fast, but nonetheless very economical, and doesn't need us to have GPUs and TPUs and so forth. So which is 1.73%. So there's a lot of data that is showing, that's been shown here. All right, so that is it. What I want you to do is go and search perhaps different data sets. Right, let me go back here. So for instance here, you can up the amount of data sets. So instead of 1,000, first 1,000 to train, you can perhaps say 10,000. So just know the more you add, the more time it will take, and go from there. Or you can go ahead and load different kinds of data sets, right? For instance, if I hover over, you can see that this comes from Hugging Face. You can just go ahead and you can search Hugging Face data set, load data sets, I should say, and you will find many different kinds of data sets that you can play around with and start training your models with. The important thing here is that we have to have the model checkpoint, which means is the model they're going to be using to train, right? Because the idea is to take an established model and then use that to train using LoRA technique to train or to fine-tune that model so that we can have different flavors per se of that same model, right? Trained on that particular data set. All right, so this is a good starting point. There's a lot, as I said, and most of this may seem very foreign, but that is the main idea. So what I would really suggest you do is to go and find different data sets, as I said, and see if you can train this model and maybe find different ways of testing the texting texts as I have here. Maybe find something different depending on what you trained your model on. All right, there you go. This is exciting, and I hope this was helpful. So we're going to continue in the next video. So we're able to train two models here. We have the LoRA sentiment and LoRA topic. Okay, very good. And I thought it would be fun to create a very simple API, a simple API service, where we're going to be able to tap into that API service and then ask questions or pass in the text and see what these models are going to predict. Okay, something simple. And if you don't want to do this, it's okay, but I will do it so you can see the applicability of such thing. And so I'm going to go ahead and create a new file here called API service.py. .py. And there are a few technologies that we're going to be looking into here. The first one is the FastAPI, which is a framework, a library that allows us to create APIs, so in Python. And also UVcorn, which is another tool that allows us to connect with FastAPI locally and run all of that. So what I'm going to do here is, let me go and say pip install those two. So pip install FastAPI and UVcorn. I'm going to do a few imports here. So I'm going to use the FastAPI, and I'm going to use base model of Pydantic. This is for make sure that we have validation of some classes that I'm going to show you here. And of course, we have transformers, PEFT, and UVcorn, and all of that. And so what we'll do is, remember, we're going to use these two, LoRA topic and LoRA sentiment, our new models, trained models, and then create some sort of an API so we can pass information through, like text, and see if it will predict correctly. So let me set everything up here. There's some classes that I'm going to set up so that it's easier for us to deal with our API when we create this API. Okay, so first of all, I'm going to create this review request, which inherits from base model. So essentially this class will have a string field called text. I have a batch review request. I'm going to have a list of strings called texts. And then I have sentiment response, which is going to be the response that we're going to receive once we send all that stuff. So I'm going to have field the text, the sentiment, the confidence, and the processing time. And then I'm going to have this batch sentiment response, which is going to give me results of a list of response, a sentiment response, and of course the total processing time as a float, right? All right, so let's go ahead and create, in this case, a class called model class. So this is going to put everything together so that we can then call it to create the actual API. Okay. So the model class here, we initialize a few things in the init function. So we using the CUDA, Torch CUDA, to run everything. And I say here, if CUDA is not available, because sometimes it's not available depending on the machine you're running, we're going to just go ahead and use CPU. Okay, the model checkpoint is always this Dilbert, distilled Dilbert base uncased. Okay. And then I have this model path here because I'm going to set up the path to the model to be used. It's going to be LoRA sentiment. Remember, all of that is this one here, which we have already. So tokenizer, model, and I'm going to use the load model. The load model, what is that? Well, it's going to load the tokenizer and the model itself. So that's what we've seen before. And to load first the base model, we're going to pass, of course, the model checkpoint, which is this guy here. We need that. And then we're going to load LoRA weights. So we use PEFT model. From pre-train, we pass the base model because we need that. And then we pass the model, which is the one that we trained on, which is LoRA sentiment. Okay, so that's how we get the LoRA weights and everything. We set the evaluation mode and then the device. So model to device, self that device. So what is that? Well, the device in this case is going to be what we put here. So it's either going to be CUDA to run this, Torch CUDA, or we're going to just use CPU. Okay, so this point you're going to say, okay, model was loaded successfully. So in this case, we have the base model and then the trained model. All are going to be together, but focusing on the trained model or the fine-tuned model. Okay, so we have the predict sentiment. This is the function that is going to allow us to predict for a single text. We go through all the things that we've seen before. And then we map the prediction to sentiment. So in this case, so if prediction is 1, there's going to be positive, else it's going to be negative. Okay, so we have processing time, so we can see then how long it took for all of that. So we put all that together and then we return as a dictionary. So we're going to have the text, the sentiment, and the confidence, as well as its processing time. All of these pieces, we're able to retrieve them from, as you can see, the part where we're getting the prediction, right? So for output, we're going to get the models, all the inputs, and then the probability. We use this long function here. We use softmax. Remember, this is a function we looked at in the time when we talked about machine learning or deep learning, right? These are different functions in which the prediction happens or can be predicted. For argmax and all of that. So the idea is that we get the prediction and we get the confidence from these calculations here. Okay, so then we have the predict batch sentiment. This is going to predict a sentiment for a batch of text. So we can have 5 or 6 or 100, and so all of that is going to go in a batch. So the same thing happens, but now it's just through a batch. Okay, so next, once we have that class, then we're going to go ahead and have the actual code specifying the API and all. All right, so here is where we initialize the model service, because we need this model service, which is what we created here, went through. So it knows how to create the model and function to predict and all that stuff. And so now this is where I'm actually going to start using FastAPI. So this is saying what? We're saying this root function is going to be called when we go to the root directory. So as you will see in the browser, we go to root directory when we're running. This is what's going to return. So what's going to return is this. Okay, the message, movie review, sentiment analysis API, status is active, endpoints, and tells us all the endpoints where we can go to check things out. All right, now the post, this is where we go. So if we go / and predict on the browser, right, then this is going to be called. So this is the predict sentiment. Now the response model we're saying here is going to be the sentiment response. That means what we are expecting to receive is going to be this object or class, which is going to be an object. So essentially we're going to have text, sentiment, confidence, and processing time. Okay, and so what happens inside here? Well, we're going to call the model service and call the predict sentiment function and pass the request text. So essentially whatever we pass in as text, we're going to pass that through the predict sentiment, and we're going to get a result. And then we have the predict path endpoint, essentially the same thing. The response model, how we want to structure the response, is going to follow this batch sentiment response. And of course, when this is called, that's when we go to this endpoint path in URL, this is what it's going to be called. This is what's going to be called. And we have this health check place here just to check how things are going, the health of our API. Okay, so now we have this uvcorn.run, and then it's going to be API service, which is this file here. Go to the app instantiation, which you see at the top here. So it's going to be a FastAPI instantiation, so we run that. Okay, let's go ahead and give a quick run. API service, hit enter. So if all goes well, we should see that we're going to run on port. There we go. So there we go on port 800 or 8000, I should say. So what I can do, we can copy this or just Control+C or Command+C, and that's going to be go ahead and open. There we go. So we have our server is running. So this is the message that we get from running, going to this 8000, port 8000 locally. Make sure this is running, and then you should see something like this. So it's a payload. It says message, movie review, sentiment analysis, active. The endpoints we can use are this. What does that mean? Well, if I go and copy that and go over here, get a forward slash and paste that, hit enter, you can see that I get here. So status is healthy, model loaded, true, device is CPU. In your case, if it's different device that it's running, it should show exactly that, if it's CUDA or whatever that is. So I'm going to go back and see. Let's say I want to go to predict sentiment. I'm going to copy this and paste that in, hit enter. Okay, so it says detailed method not allowed, right? Because we are in the browser. So in the next video, I'm going to write yet another file, Python file, that will interface with our API endpoint here. All right, so we have indeed our API working here. Of course, we can't do predict batch or predict because these are post methods, so it won't work on the browser for security reasons. So this is why I'm going to create another file which is going to allow us to use this API and check it out. So down here, I'm going to go ahead and create yet another file inside, say fine-tune LoRA, and I'm going to say test API.py. Not a very exciting name, but that works. So what are we going to do here? Well, I have all the code. So first of all, I'm going to go and do some importing here. So I'm going to use the requests, which allows us to do requests to an API or server. All right, so and then I have a function which I'm going to put here real quick. So this is called the test API function. So remember, our API endpoint is localhost 8000. This is very important, and we know this because that is the 8000 as you see here. So that is our base URL. Okay, so now I have this test single prediction. I have this is the input that is expecting, which is a dictionary with key text, and then value is going to be whatever we put here. So it's going to be, this movie was absolutely amazing, great performance by all actors. And then I'm going to go ahead and say, hey, testing single prediction. And then what happens, I'm going to use request and say post, because that is the function method we need to pass along, and pass the base URL, which is this, and then append predict. So essentially I'm saying I'm going to go to the predict endpoint. Okay, single review. So the JSON that we're going to pass along is going to be this single review to post into the API and hopefully get a response. Okay, so then we are going to get the JSON response. I'm going to put say JSON dumps just to make this an actual object, right? JSON object. So serialized object to a JSON formatted string. That is. All right, and then we have the test batch prediction also. This is going to be batch reviews. So it's going to be a list or an array that contains different texts. So this movie was absolutely amazing, and terrible movie, waste of time and money, pretty average movie. And I can add yet another one here. I can say it was okay, I've seen better, something like that. Okay, and of course we're going to go ahead and test that endpoint predict batch. Okay, so we're using all of the batches, or rather all of the endpoints, just to test it out. All right, so let's go ahead and then call the test API and see how this works. So make sure, of course, that the API is still running. I have it running still successfully, and open a new console here. So we have two. This is where everything is running, and this is where we are going to run again. So I'm going to go ahead and then say Python. So moment of truth here. Let's check it out. So we passed everything. It worked because you can see the results here. So now testing single prediction. So this movie was absolutely amazing. Great performance by all actors. Sentiment is negative. Okay, so that's terrible because that's not true. And confidence is 99%. Right? So that's one case that you remember we saw earlier, that sometimes it doesn't catch all of the use cases here. That's okay. Let's look at what happens to this testing batch prediction. So first of all, we have this movie was absolutely amazing, great performance. We get this negative, which is not true. And then terrible movie, waste of time and money, negative, sentiment negative, which is true, right? And gives us process time, all of them, of course. And the confidence. So 99.7% of confidence. And then pretty average movie, nothing special. So I would say that is kind of negative, which is kind of true, I would say. It was okay. I've been seen better. That's also negative. Okay. So maybe I should add something else that will make it a little bit positive to make this work. Now, this tells you that perhaps the sentiment analysis or the sentiment model that we trained, it didn't do well, because I think it was about 80% or 60, between 60 and 70% of accuracy when we saw earlier. And so of course that would probably need a little bit more training, which means you would have to go back and up the amount of data sets, the amount of data points or data, instead of 1,000, maybe 5,000 or 6,000, something like that. Okay. So that's what we have here. It doesn't have all of the answers, of course, but you can see that this is actually working. So what you want to do, or you could do, is perhaps generate more positive things here to see how this would work. So what you could do also is perhaps create more use cases here for testing and just testing things out. But what's important to know is that our API is actually working. Right? So we have an endpoint that when we pass some text, it's able to give us a payload with the sentiment, the confidence of the model, to say that is how confident I am that this, for instance, is negative, and the processing time. So what I want you to do for this case, this API is using, let me go back, I believe that it's using the LoRA sentiment. So you can change this path to You can see here I have LoRA sentiment improved because in my testing, I added more testing or training or fine-tuning to improve LoRA sentiment because it wasn't doing well. So you can do that again, like I said, run again the model to make sure that you fine-tune that with more data sets and see how that works. Or you can take all of this and change this instead of LoRA sentiment, and you can use this other model, which is LoRA topic. We saw that performed real well because it did real well in the evaluation when we did fine-tuning. In any case, this is just a good starting point for you to start exploring these things. And I really consider you to really explore fine-tuning, especially at this level, because it will give you more ideas. It will actually force you to do more research, trying to figure out what all of this means, which is exactly what I want you to get out of this, is to figure out how all of this means and start breaking things, right? It's pretty fun. All right, now we're just having fun. So next I'm going to chat with the FT models, the fine-tuned models that we created. So I'm going to create a very simple interface here. It's not a big deal, but something to show off our hard work. So let me go ahead and get all the code so I can explain what's going on. So it's very simple again, so don't fret. So no worries. Okay, so I have this model interface here. So this is where I'm going to put together, we are putting everything together, right? To set up the tokenizer, the sentiment model, the topic model. So we're going to use both of these models and set up a chat so we can go from there. All right, so we're going to load the models. We've seen this before. It's just a different format here. So load model. We're going to load the sentiment model, right? We know what that is. And then we're going to load the LoRA topic models. So we do all of that. And then we have the analyze text. So I'm not going to go through explaining everything because you've seen this before, but essentially we are setting everything up for analyzing the text that comes in. So the model type, if it's topic or both, then we go through the process of selecting and mapping everything, all right? And return the results. All right, so then we have this print welcome. So this is going to be just what users are going to see and allow us to give options to start interfacing with our models. And so let's go ahead and define the interface function here. So we instantiate the model interface as you saw above, and then we start loading the models. And mode in this case is going to be both, just as a default to interface or to talk or chat with both models. And then we have this chat interface here, which allows us to input the text that we want to analyze, right? So it's going to handle some commands if we want to exit and help or whatever it is that we want to allow users to do and get help with. All right, so that's exactly what we're doing here. And then we go to the text analysis. So we call the analyze text. We pass in the text that needs to be analyzed and the mode as well. And if we have results, we're going to go ahead and show all of those results. So the sentiment, the confidence, and all of that. Okay, let's go ahead and run this quick. All right, so we did all the things that need to do. You can see welcome to LoRA model chat interface. Nice. So the interface allows you to analyze text for sentiment analysis, positive or negative, topic classification, world, sports, business, science, etc. And quit or exit to end the session, switch to change analysis mode, and so forth. So current mode is both. So enter the text to analyze. Wow, very cool. Let me see if I can find some nice text here. Okay, I have some. I'm going to just paste. We've seen this before. Tesla stock surges 20% after strong quarterly earnings report. Let's go ahead and analyze. Look at that. Looks like results says negative. Confidence is 99%. The topic for the topic business is confidence is 92%. So that's pretty good. Sentiment is negative, right? 20% I guess is pretty bad. So that's good. And let's try a different one here. Maybe something we've done before. Another one. That one. New AI model achieves breakthrough in protein folding. Okay, so sentiment, I guess it says negative. Maybe it's sort of neutral, but that's okay. We only have two options. And topic is indeed science, technology. Confidence is 98%. All right, let's try something else we've seen before. Okay, so results, sentiment is negative. Very good. For what? For, right, the worst movie ever. Complete waste of time. So results, sentiment is negative. Yes, that's true, 99.8%. The topic is world. That makes sense. It's about a film, a movie. Yeah. Okay, so it kind of works, doesn't it? So let's see if I say switch, what's going to happen? Switch. Enter the name of mode, the new mode. I'm just going to say topic. Okay, so now it's going to just focus on the topic. Let me do again another one. Should give me the same results at least. So topic is science, technology, confidence 98%. Okay. All right, I won't continue, but you can see how fun this is because we were able now to, in many ways, different ways from API through an API, as well as just creating this nice chat box here where we can interact with our models that we pre-trained, or rather that we fine-tuned. This is very exciting. It's a very small scale, but I hope you're seeing how fun and the power and use cases that you can use this for. Play around with this, think of other use cases, and go ahead and do stuff, break stuff. This is why we do this. All right. Thank you. I'll see you next. Now, because this is too much fun, I have this other file here. This is the last one where we're going to put everything together. So I have this train and chat. So the idea is that we're going to be able to put everything that we learned so far, which is training the models, as well as going ahead and start chatting with it, giving all the options. Now, this is a little bit more comprehensive because I also have this universal device set up. Depending on what you're running, Windows, Mac, Linux, and so forth, some of these devices may not be available. So for instance, through Torch, CUDA, if it's available, then it's going to be used. It's going to go ahead and use GPU, in this case, CUDA, which is going to return the device CUDA, right? If, for instance, the platform is Darwin and MPS is available, then it's going to go ahead and do that. So this is going to be good for Mac, M1 and M2 and M2. Okay. Else is going to just go ahead and use a CPU for processing. Okay. So this is very, it's just a way to put things into perspective, put it together. That way we don't run into issues. All right. So I have here this model metrics. So I'm going to be setting all the metrics as a dictionary. So all the parameter, original size, LoRA size, memory usage, trainable params, and all of that. And then I have this model trainer. So this is what we've seen before. It's going to go through the process of setting everything up, the checkpoints, which is the BERT, the still BERT based uncased model that we are going to be using as the main model that we're going to be training or fine-tuning. And we do all of these things that I'm not going to go over things. But a few things I've noticed here I have done, you will notice. For the IMDb load set, I'm doing 2000 at this point. So remember, the more items you're training on, the more pressure we will give to our device, in this case, our machine. Okay, so, and it may take a little bit longer. And I do the same thing. But one thing, notice also, I'm adding these custom movie examples. So these are additional examples I would add to train our model. Okay, so I absolutely love the new Spider-Man movie. And the movie was fantastic, amazing visuals and all that stuff. Okay, so, and then we add all those labels to say for each one of these. So 1, 2, 3, 4, 5, 6, 7, 8. So 1 to be positive. So this is a positive, and 0 is going to be negative. So this one here, and this one, all of these, the labels that we're attaching to it is negative, okay, because there are negative sentiment. All right, so we do all that information, that stuff to add columns, remove columns, and set everything up for our data set and all of that. We go through the pre-training and building and do all the things we've seen before, right? And you can see here the function train. It takes the training arguments, create those arguments, and then pass it all through, and all the process happens. But what also you want to see here is that I have this print training summary. So for this, you have to have this pretty table, which is a dependency called pretty table. So I have added here. So say pip install and get pretty table. What that does, well, it just makes things prettier and looking good for our metrics here. All right, we have the model interface. We're putting everything together to load the models, how to do that. Notice that we have this load LoRA sentiment improved for this time that we run this. Now, in your case, you're going to go ahead and run this. I'm going to go all the way, run this, and then you're going to get these options on what to do and all of that. So let me go ahead and run this. It will take a little bit, but it's all good. Train and chat. So it's going to go ahead and tell me exactly what's going on here. So you can see that movie review sentiment analysis system, and it gives me all that information. And then it says that system information, operating system is Darwin, and Python version is 3.12. The Python PyTorch version is 2.6, and CUDA available is false. I don't have CUDA, I have GPU, but it's using MPS available is true, so just CPU. And now I have the option of training a new model, analyze reviews using existing model, or exit. So this may take a while. I'm just going to go ahead and start from scratch. Say 1, train new model, hit enter. So this is going to go through the whole process you've seen before. Nothing really new. It's going to load the IMDb dataset and go through the process. So I'm going to pause the video and wait until everything is done. So on your end, when you run this, just be patient. Make sure that you let it do its thing. Okay, so after training everything, you see we have this training summary. Let's go down to see the whole training summary. So metrics here. So training time was about 272 seconds. So it took a little bit. And the memory that was used was about close to 2 gigabytes, I believe. Okay. Or a little over 2 gigabytes. And then total parameters, we have 68 million, over 68 million. Now, trainable parameters is about 1.2 million parameters. So the compression ratio is 57.65, and the final accuracy, it says here 100%. Okay, that's fine. All right, now that we have everything, you can go here. You can see that now we have checkpoints. We should have a bunch of them, down to 606 and 3, I should say. And then we have LoRA sentiment was updated. Now we have this LoRA sentiment improved, which is going to use what we have improved upon. So we have 1, 2, and still have the topic, LoRA topic models. So now let's go to analyze reviews using existing model. So I'm going to use number 2, for instance, and enter something for us to review. Let's say I want something that says, so the worst film I've ever seen. So, of course, you can see that sentiment is negative. Confidence is 82%. It should be higher confidence because it's negative, right? But that's fine. So that works. I'm going to add this left field here. Tesla stocks surges. Let's see what's going to do. Okay, it's still negative. That's pretty good. And let me go back and have something that's supposed to be positive. Let's see how this will behave. So this movie was absolutely fantastic. The acting was superb. Let's see. So we have a problem here. It's not quite giving us the correct result, but that's okay. So that's part of testing and fine-tuning our models. And you can see the confidence is 80% and sentiment is negative, which is not true because sentiment is actually positive. The movie was absolutely fantastic. The acting was superb. But that's fine. All right, so at this point here, I've given you a lot of things to think about, a lot of tools for you to play with. We are done. So you've learned how to use LoRA technique to quickly, in many ways, train or fine-tune models, right? We fine-tune a small model, base model, and create different pieces of models that are fine-tuned from that base model. And we are able to use that and play with that and test things out and see how it all works. Thank you, and I'll see you next. All right, so I hope this was helpful. You were able to really dive deep into fine-tuning, understanding what is fine-tuning and why would you want to fine-tune your large language models, and the use cases as well as the strategies and different tools to do so. And And I hope now you're able to go and fetch a large language model somewhere and fine tune to your liking. Thank you so much for being here. And again, this is part of a larger course, 28-hour plus course on AI and large language model engineering. So we go from not knowing what AI, what large language models are, to understanding how to really leverage large language models, but understanding how it all started. Machine learning, deep learning, understanding what the transformer architecture is, and all these things. And of course, ultimately understand how to build on top of large language models, which is build AI-based applications. So it's a full-on course, and I would love to have you. There's a link in the description. Go ahead and enroll. It's at a huge discount right now. I think it's 75 to 80% discount. And so I hope you enroll, and I'll see you next time.